Hello there and welcome to the Sleepy Explainer, where the universe is explained like a curious mind drifting into rest, with a touch of an imaginary world. What if I told you today that long before the age of dinosaurs, before the mighty Tyrannosaurus or the towering Brachiosaurus ever took a step, there were creatures that ruled the earth, vanished almost completely, and then, astonishingly, returned. This is the story of animals that lived twice, not in the sense of reincarnation, but in the very real evolutionary struggle where entire lineages rose, fell to extinction, and then re-emerged to dominate once again. The Earth, in its deep history, has never been kind. Across billions of years, our planet has staged 5 major mass extinctions, catastrophic episodes that erased most life. But here's the fascinating part. Some animals didn't just survive once. They came back after multiple collapses, reinventing themselves each time. Paleontologists call this resilience, but when you study the fossils, it almost feels like persistence against the odds, a stubborn refusal of life to vanish. To understand this idea, we need to rewind to the Paleozoic era, over 300 million years ago. This was a world radically unlike our own. Continents were shifting, the climate swung wildly, and oxygen levels soared higher than today. Vast swamps covered the land, teeming with amphibians the size of crocodiles, insects as large as hawks, and strange reptiles that looked like they were halfway between lizards and mammals. It was a world of experimentation. Evolution was trying out blueprints, testing who could thrive on land, who could rule the seas, and who could bridge both. And yet, every time life seemed to settle into balance, disaster struck. Volcanic super-eruptions darkened the skies, asteroid impacts boiled the oceans, and shifting climates dried lush swamps into barren deserts. Entire ecosystems collapsed. But here's where the living twice story begins. Many of these lineages should have ended forever, but they didn't. Take the temnospondyls, giant amphibians that looked like salamanders on steroids. They flourished in the Carboniferous swamps, nearly disappeared during extinction events, only to re-emerge millions of years later as top predators again. Or the Dicynodonts, tusked plant eaters that seemed doomed in the Great Dying, yet returned in the Triassic, becoming one of the most successful groups on Earth. These were not brief flickers of survival, these were comebacks, with each return reshaping ecosystems anew. This concept that evolution doesn't just progress in a straight line but loops back, reviving old ideas, is what makes pre-dinosaur history so mesmerizing. To study these animals is to study resilience itself. They are proof that life on Earth is never entirely erased. It waits, adapts, and when the chance arrives, it rises again. And as we step into this story, we'll see how deserts once turned to seas, swamps became graveyards, and creatures who should have been gone forever lived twice. So, we've set the stage with the idea of creatures living twice, but now comes the real question. What kind of world could create such cycles of death and rebirth? To understand why so many lineages before the dinosaurs vanished and re-emerged, we need to look closer at Earth itself, not as a stable blue marble, but as a restless, ever-changing planet. Picture this. 500 million years ago, the continents weren't scattered across the globe like they are today. Instead, they were constantly in motion, colliding, breaking apart and drifting like giant rafts across a planetary ocean. This slow but relentless dance, what we call plate tectonics, meant that no ecosystem was permanent. Forests could become deserts, shallow seas could turn into mountain ranges, and tropical swamps could be buried, compressed, and reborn as coal beds millions of years later. During the Ordovician period, around 450 million years ago, much of the Earth's surface was submerged under warm, shallow seas. Imagine enormous trilobites crawling across seafloors carpeted with sponges and corals, while armored, jawless fish darted in the currents. This was a water world, teeming with life, but it was also fragile. When ice sheets expanded across the planet, sea levels dropped dramatically, draining those shallow seas and wiping out countless species. The oceans themselves seemed to vanish from certain places, leaving behind cracked seabeds and salt flats. But life adapted. As the continents shifted again, the seas returned, flooding the land and offering new habitats. Old groups resurfaced, almost as if given a second chance. It's here we begin to see one of the great themes of Earth's history. Extinction is rarely the end of the story. Instead, it often clears the stage for familiar actors to step back into the spotlight in new forms. And here's the haunting part. If ancient life could return after near total annihilation, what about ideas? Could an alien civilization, perhaps, have seeded Earth not once, but multiple times? Could 3i Atlas, that strange visitor from interstellar space, be a continuation of an old dialogue, one that began when the continents were still locked together? As Earth's crust heaved and the first deserts dried, those seas that became sand may have buried more than ancient water. They may have hidden secrets, fossils, artifacts, or even signals, waiting for someone to rediscover them. And that brings us to the next chapter of our journey. Because while oceans vanished and deserts spread across the land, another story was quietly beginning. One written in the fossils of creatures that refused to stay gone. So, what exactly crawled out of those shifting seas to walk across the barren deserts of an ancient Earth? And why do scientists sometimes describe them as ghost lineages? When deserts swallowed seas, not all life vanished. Some creatures clung on, adapting to the new conditions in ways that still puzzle scientists today. This is where we encounter one of paleontology's strangest ideas, the ghost lineage. A ghost lineage is a kind of scientific mystery. Imagine finding fossils of a creature in rocks 400 million years old, then nothing, no trace, for tens of millions of years. Suddenly, in younger rocks, the same creature appears again, as if it had skipped chapters in Earth's book of life. Where was it hiding? How did it survive unseen while the world transformed? Take the coelacanth, for example, a lobe-finned fish first appearing over 400 million years ago. Its fossils vanish from the record around 66 million years ago, right at the end of the age of dinosaurs. For decades, scientists believed it had gone extinct alongside them. Then, in 1938, fishermen off the coast of South Africa pulled a living coelacanth out of their nets. It was like finding a living fossil, a creature that had cheated extinction and returned from Earth's deep past. Now imagine this same kind of survival, but happening millions of years earlier, in the chaotic world before the dinosaurs. Fossil evidence suggests that amphibians, early reptiles, and certain fish vanished during global extinctions, only to reappear later in the fossil record. They didn't evolve from scratch again. They simply persisted in hidden corners of the Earth, perhaps in isolated seas or sheltered valleys, then expanded once conditions allowed. These ghost lineages force us to ask, how much of Earth's story are we missing? If deserts can erase seas, then whole worlds of living creatures can vanish from the record, leaving only fragments behind. The Earth we think we know, mapped neatly through fossils, might actually be full of blind spots, vast stretches where life continued unseen. And here's where things get even more intriguing. Ghost lineages don't just hint at resilience, they suggest cycles, almost as if nature itself has a memory. Entire groups of animals step off stage, only to re-emerge when the environment shifts. It's a rhythm: extinction, survival, return, echoing through deep time. But could there be more to this rhythm than chance? Some scientists argue that mass extinctions act like filters, allowing only certain life forms through. Others wonder whether external forces, from asteroid impacts to cosmic visitors, reset the stage in ways we don't yet understand. What's certain is this: when life reappears after long absences, it's never quite the same. It carries the imprint of survival, of hidden evolution. And in these gaps we find some of the strangest creatures Earth has ever known. So let's open the fossil record again and meet them, starting with animals that look like they've lived not once, but twice. If ghost lineages remind us of Earth's missing chapters, then amphibians are the creatures that somehow managed to write across them. Before the age of dinosaurs, before mammals, even before the dominance of reptiles, amphibians were rulers of the land and water. And against all odds, some of them managed to survive not one, but multiple planetary crises. Let's rewind to the Carboniferous period, over 300 million years ago. Back then, much of Earth was a swampy paradise. Towering trees with trunks as thick as houses stretched into humid skies, while dragonflies with wingspans wider than a dinner plate buzzed through the air. In this world, amphibians thrived. They were the apex predators, enormous salamander-like beasts, some growing more than 6 feet long. But this golden age didn't last. As the planet's climate shifted, those lush swamps began to dry. What were once vast wetlands turned into deserts. For many creatures, this meant extinction. But amphibians found a way through. Fossils suggest that while many species perished, others adapted, retreating to rivers, lakes, and coastal zones where water still lingered. One of the strangest survivors was the temnospondyls, a diverse group of amphibians that looked like crocodiles with frog-like heads. These creatures appeared in the fossil record before the dinosaurs, and astonishingly, some lineages survived well into the Triassic, overlapping with the very first dinosaurs themselves. They lived twice, once in the Carboniferous swamps, and again in the deserts and shifting landscapes millions of years later. What's remarkable about these amphibian survivors is not just their endurance, but what they reveal about evolution. Amphibians are highly sensitive to environmental change. Modern frogs and salamanders are often the first to vanish when ecosystems collapse. Yet, in deep time, their ancestors clung on through some of Earth's most violent upheavals. How did they do it? Some paleontologists suggest that amphibians' dual lifestyle, part land, part water, gave them flexibility. When seas dried up, they could retreat into shrinking rivers. When deserts expanded, they burrowed or remained in shaded wetlands. They were the shapeshifters of prehistory, bending with the environment rather than breaking against it. This endurance made amphibians witnesses to cycles of extinction and rebirth. They bridged one world of life into another, carrying genetic legacies across millions of years. Without them, much of Earth's story might have been cut short, but amphibians were only the beginning. To truly understand how animals lived twice, we need to turn to the early reptiles, creatures that took survival a step further, evolving new ways to dominate the changing Earth. While amphibians clung to the margins of survival, something entirely new was stirring in Earth's ecosystems. Around 310 million years ago, the first true reptiles appeared, small, unassuming creatures no bigger than modern lizards. At first glance, they may not have seemed extraordinary, but in reality, they carried with them an evolutionary innovation so powerful that it would forever reshape life on land. That innovation was the amniotic egg. Unlike amphibians, whose eggs had to be laid in water, reptiles encased their developing young in a protective shell. This meant that for the first time, vertebrates were no longer tied to rivers, lakes, or swamps for reproduction. They could march inland into forests, plains, even deserts, ecosystems that had been completely off-limits to amphibians. This single adaptation cracked open a new chapter of Earth's story. Reptiles could live in dry, hostile environments and still thrive. They weren't just surviving, they were colonizing new worlds. Fossil evidence shows that early reptiles, such as Hylonomus, were insect eaters, scurrying through fallen logs in Carboniferous forests. But within a few million years, their descendants diversified into predators, grazers, and everything in between. They became the ancestors of creatures that would later split into two grand evolutionary branches, one leading to mammals, the other to dinosaurs, crocodiles, and birds. This was the first true reptilian revolution. Animals that didn't just survive twice, but lived in multiple worlds. They endured the drying of Earth's swamps, adapted to deserts, and then went on to dominate entire ecosystems. Unlike amphibians, they didn't just bend under pressure, they transformed. It's important to realize how radical this change was. Imagine the Earth of the late Carboniferous, the climate shifting, swamps collapsing, amphibians gasping in shrinking pools. Into that chaos, these new reptiles stepped forward, carrying their survival strategy inside their eggs. They weren't merely inheriting the Earth, they were engineering a new blueprint for life itself. What's even more fascinating is how quickly they expanded. Within tens of millions of years, a blink on the geological clock, reptiles had taken over niches across the globe. By the dawn of the Permian period, they were already rising as the dominant force of terrestrial ecosystems. And yet, their story too was about to be tested. The Earth would soon face the most catastrophic extinction in its history, the Permian-Triassic extinction, when nearly 90% of all species vanished. But reptiles weren't just participants in this drama. They were the survivors, and in the aftermath, their resilience would set the stage for the greatest evolutionary dynasty of all, the dinosaurs. But if reptiles thought they had secured their eternal reign, the Earth had other plans. The stage was set for one of the darkest chapters in our planet's history, a catastrophe so immense that it would be remembered as the Great Dying. Imagine standing on the shores of a shrinking inland sea, the once vibrant waters now reduced to briny puddles. The air grows heavier with each passing year, temperatures soar, and volcanoes spew unrelenting columns of ash into the skies. This wasn't just another shift in climate, it was the single most devastating extinction event our world has ever seen. Around 252 million years ago, near the end of the Permian period, Earth was pushed to its breaking point. Vast volcanic eruptions in a region we now call Siberia released titanic amounts of carbon dioxide, sulfur dioxide, and methane. These greenhouse gases wrapped the planet in an oppressive heat-trapping blanket. Ocean waters warmed dramatically, oxygen levels plummeted, and ecosystems that had thrived for hundreds of millions of years began to collapse. It wasn't just hot, it was apocalyptic. Oceans turned into stagnant, poisonous basins. With little oxygen, sulfur-loving microbes took over, releasing clouds of hydrogen sulfide gas that poisoned the seas and may have even leaked into the air, suffocating life on land. Scientists estimate that over 90% of all species on Earth perished during this period. Imagine 9 out of every 10 creatures vanishing forever. Entire coral reef systems, trilobites that had survived for 250 million years, and countless amphibians that once ruled the wetlands. The Permian extinction was so severe that it nearly ended multicellular life as we know it. For a moment, it seemed Earth might remain a barren desert world, stripped of its vibrant ecosystems. But life, in its stubborn persistence, refused to vanish completely. Some species endured. Burrowers that could hide beneath the parched surface, hardy plants clinging to rare patches of moisture, and a few resilient reptile lineages. These were the survivors of the worst ecological collapse in history. The world went quiet, ecosystems reset, and evolution was forced to start again almost from scratch. But here's where the story turns. From the ashes of destruction, new opportunities would rise. The survivors of this cataclysm were not just clinging to life, they were about to reshape it. Out of the silence left by the Great Dying, the Earth seemed empty. Vast deserts stretched across Pangaea, the supercontinent, their red sands whispering of a planet stripped bare. But in those desolate landscapes, something remarkable was beginning. Life, against all odds, was stirring back to its feet. This was the Triassic period, beginning around 252 million years ago, a time when Earth was reshaping itself. For millions of years after the catastrophe, ecosystems remained unstable, fragile like glass ready to shatter. Yet it was in this crucible of scarcity that new forms of life began to carve out opportunities. In the absence of the dominant amphibians and other Permian giants, reptiles took the stage. Some were small, darting insect eaters. Others grew larger, adapting to fill the empty niches left behind. Unlike amphibians, reptiles were tougher, better suited to the drier climate of Pangaea. Their amniotic eggs, which could survive without needing constant water, gave them a decisive advantage in a world where lakes and rivers had all but disappeared. Among these early pioneers were the archosaurs, a group of reptiles that would eventually give rise to both crocodiles and, much later, dinosaurs. At this moment in history, however, they were only just beginning to spread, slender-bodied hunters with sharp teeth and long tails. With every passing million years, plants reclaimed barren ground. Hardy conifers and ginkgos rooted themselves in dry soils, slowly greening the desert expanses. Insects followed, buzzing in renewed swarms, and behind them, the food chains began to reassemble, predators and prey rediscovering balance. But these were fragile ecosystems. Imagine rivers running dry without warning, forests vanishing in sudden droughts, or floods that swept entire valleys. Earth was still unstable, still recovering from the chaos. Each generation of creatures walked a knife's edge between survival and extinction. Yet within this fragile rebirth, evolution was planting seeds that would eventually reshape the planet. Tiny lizard-like creatures darted across dry plains, some no bigger than your hand, while larger predators stalked the shadows. It is here, in the Triassic, that the first true ancestors of the dinosaurs appeared, small, agile, and unremarkable at first glance. No one could have guessed then that these modest survivors, rising from the ashes of the great dying, would someday dominate the planet. As life clawed its way back from the edge of extinction, the Triassic world became a laboratory of bizarre experiments. Evolution, given a blank canvas, began sketching creatures that looked more like ideas than animals. If you wandered through a Triassic forest or along the banks of its rivers, you might wonder whether you had stepped onto another planet. One of the most striking predators was Tenosauriscus, a reptile with a towering sail stretching across its back. Imagine a crocodile-shaped body balanced on long legs, but crowned with a spiny sail larger than its own body. Scientists debate what this feature was for. Perhaps a thermal regulator, absorbing and releasing heat in a world of wild climate swings, or perhaps a visual signal, intimidating rivals or attracting mates. This was the age when survival depended not only on claws and teeth, but also on adaptation to a hostile and unpredictable Earth. Meanwhile, in shallow waters and coastal lagoons, the placodonts thrived. These strange reptiles had broad, flat teeth like paving stones, perfect for crushing the shells of clams and mussels. They resembled a cross between a turtle and a seal, with stubby limbs and armoured backs. Some scientists even consider them precursors to later marine reptiles, laying the groundwork for creatures that would one day rival whales in size. Not all Triassic reptiles looked alien. Some, like the early phytosaurs, bore a striking resemblance to crocodiles, complete with long jaws lined with teeth. But here's the twist. Phytosaurs weren't crocodiles at all. They were a separate branch of reptiles, evolving in parallel, filling the same ecological roles millions of years before true crocodilians appeared. Evolution, it seems, has a habit of repeating itself. You might ask, why did so many unusual body plans appear in this era? The answer lies in opportunity. After the Great Dying, ecosystems had gaping holes. With less competition, new adaptations, no matter how strange, had a chance to succeed. It was natural selection unleashed, producing diversity from chaos. And then, quietly at first, they arrived. Not the towering giants we imagine today, but small, wiry hunters darting through the ferns. These were the earliest dinosaurs, and they didn't dominate their world. Not yet. Instead, they were survivors, opportunists, slipping into niches others hadn't yet claimed. The first known dinosaurs, Eoraptor, Herrerasaurus, and Staurikosaurus, lived around 231 million years ago in what is now South America. They were barely bigger than a large dog, weighing only 20 to 30 kilograms. Yet these animals carried the blueprint that would one day conquer Earth: lightweight skeletons, fast-moving legs, and a metabolism that burned hotter than most of their reptilian neighbors. Imagine one of these creatures weaving through Triassic underbrush, tail stiff for balance, jaws snapping at small lizards or insects. It wasn't a king yet, but it was quick, clever, and built for a changing world. And then, the Earth itself delivered the opportunity. Around 233 million years ago, the Triassic world stumbled into one of its quiet but devastating crises, the Carnian pluvial event. For nearly 2 million years, the climate seesawed violently. Long droughts gave way to sudden, catastrophic floods. Volcanoes belched carbon dioxide, choking the skies. Entire ecosystems collapsed. Imagine being one of those early predators, the phytosaurs by the rivers or the sprawling reptiles that once seemed unbeatable. Suddenly, Rivers dried up, then returned as torrents that drowned nesting grounds. Plants withered, then regrew in strange new forms as rainfall patterns shifted. The very rules of survival were rewritten, and for most large reptiles, it was too much to adapt to. But make no mistake, the Triassic wasn't theirs alone. They had competition everywhere. Phytosaurs ruled the rivers. Sail-backed predators like Catenosauriscus prowled the plains. Early mammal relatives still scurried underfoot, staking out the night shift. Dinosaurs weren't inevitable rulers. They were just one set of players in a crowded ecosystem. Their early success came not from brute force, but from flexibility. They could run faster, conserve energy more efficiently, and adapt quickly to the Triassic's extreme heat and unpredictable droughts. What gave them this edge? Scientists point to the structure of their hips and limbs, allowing a fully upright stance. While most reptiles sprawled sideways, wasting energy, dinosaurs stood tall, their legs directly under their bodies. This meant they could run longer distances without tiring, giving them an advantage in both hunting and escaping predators. Another secret may have been their respiratory system. Evidence suggests early dinosaurs had bird-like lungs with air sacs flowing through their skeletons. This allowed for more efficient oxygen exchange, critical in a world where oxygen levels were still lower than today. But the small, lightweight, adaptable dinosaurs? They thrived in the chaos. Their efficient lungs and upright legs gave them stamina in an oxygen-poor, volatile climate. Their generalist diets allowed them to scavenge, hunt, or forage as needed. In other words, they were built for change. This wasn't the great dinosaur takeover yet, not the age of giants, but the Carnian pluvial event pruned the competition. Many dominant reptile groups shrank or vanished entirely. Ecological niches lay empty, hunters to replace, herbivores to step in for, landscapes wide open for innovation. And dinosaurs, once just background players in the Triassic story, began to multiply. They spread farther, diversified faster, and slowly began weaving themselves into every corner of the ecosystem. Today we see evidence of this shift in the fossil record. Dinosaur footprints become more frequent after this event. Species like Plateosaurus, a large early sauropodomorph, suddenly flourished. Within just a few million years, dinosaurs went from fringe oddities to recognized staples of the Triassic landscape. Scientists often call this period the dawn of dinosaurs. Not because they suddenly appeared, but because here, finally, they began to rise above the noise. The extinction of their rivals wasn't just a lucky break for dinosaurs, it was a complete rewriting of the ecosystem. Before the crisis, dinosaurs were bit players, surviving in the shadows of dominant Rauisuchians and other reptilian giants. But when the environment changed so violently, the rules of survival changed with it. Suddenly, speed, efficiency, and adaptability became the traits that mattered most. And those just happened to be the traits that dinosaurs had quietly been refining for millions of years. In the aftermath of the Carnian pluvial event, landscapes were stripped bare and ecosystems reset. Huge predators that once ruled the floodplains vanished, leaving open ecological niches, places in the food web that no one was left to fill. Dinosaurs didn't waste time stepping into those roles. They weren't the only survivors, of course. Crocodile ancestors, early mammals, and amphibians made it through as well. But dinosaurs had the perfect evolutionary toolkit to take advantage. What gave them that edge? For one, their upright posture meant less energy wasted when running and hunting. Their efficient lungs allowed them to endure environments that were harsher and thinner in oxygen, and many of them traveled in herds or groups, which added protection and multiplied their survival chances. These weren't just isolated advantages. They worked together like gears in a well-oiled machine, giving dinosaurs a head start in the race to dominate Earth. As plant life recovered and forests regrew, herbivorous dinosaurs like Plateosaurus expanded rapidly. These were not the tiny shadow dwellers of the Triassic dawn. They were large, powerful animals that could grow over 25 feet long. Predatory dinosaurs like Coelophysis rose alongside them, lean hunters who moved in packs, able to bring down prey much larger than themselves. Fossil beds show sudden explosions in their numbers, a sign that dinosaurs weren't just surviving. They were multiplying, spreading, and embedding themselves firmly into every corner of the recovering ecosystems. For the first time in Earth's history, the balance of power shifted toward dinosaurs. What began as scattered survivors had now become the central players in the Triassic drama. This wasn't yet the age of dinosaurs that would follow in the Jurassic and Cretaceous, but the foundation was set, and it all happened because catastrophe cleared the stage and dinosaurs were ready to step into the spotlight. Just when dinosaurs were starting to secure their foothold, evolution took another daring leap. Not only were they thriving in the aftermath of crisis, some began to grow to astonishing sizes. Within only a few million years, the world that had once been dominated by small, fleet-footed hunters was filling with giants that towered over the landscape. The first wave of these giants were sauropodomorphs, the ancestors of the iconic long-necked dinosaurs we all know. Plateosaurus, for example, stretched nearly 30 feet from nose to tail, dwarfing most other land animals of its time. Their size wasn't just an accident of growth, it was a strategy. By growing larger, these early sauropodomorphs could reach vegetation that no other animal could touch, monopolizing a food source that was otherwise untapped, and once an animal reached a certain size, few predators could hope to bring it down. But size came with challenges. A massive body requires efficient ways to process food and to keep oxygen flowing. Fossil evidence suggests these early giants evolved air sac systems similar to modern birds, allowing their lungs to circulate oxygen with remarkable efficiency. Their long necks may have contained a network of air sacs too, reducing weight and making it easier to lift their heads into the treetops. This adaptation was revolutionary. It was one of the keys that would later allow sauropods, their descendants, to become the largest land animals in Earth's history. Predators weren't standing still either. As herbivorous giants expanded, carnivorous dinosaurs evolved to match them. Coelophysis and its relatives honed their hunting tactics, working in coordinated packs to target vulnerable juveniles. Speed and intelligence became as important as brute force. For the first time, Earth's ecosystems were locked into a predator-prey arms race that would only intensify in the millions of years to come. It's worth pausing here to recognize how fast this transformation happened in geological terms. Just a few million years earlier, dinosaurs were small survivors in the shadow of greater reptiles. Now they were stretching into giants, altering landscapes, shaping ecosystems, and rewriting evolutionary possibilities. The rise of the giants wasn't just a milestone in dinosaur history, it was the opening chapter in a new era. The Triassic world, once dominated by uncertainty and collapse, was becoming a crucible for innovation. Dinosaurs had not only survived the storm, they were beginning to bend the rules of life itself. The rise of dinosaurian giants didn't happen in a vacuum. While animals were experimenting with size, speed, and survival strategies, the Earth itself was shifting under their feet. The late Triassic world was a planet of extremes. Volcanic rifts splitting apart supercontinents, climates swinging wildly between drought and flood, and ecosystems constantly being reset by catastrophe. One of the most defining events was the breakup of Pangaea, the massive supercontinent that had kept land animals largely connected. As tectonic forces began tearing it apart, rift valleys opened, seas intruded, and climate zones fragmented. Suddenly, life that had once shared similar conditions across vast distances now found itself in isolated pockets. That isolation was evolutionary fuel. Dinosaurs in one region adapted to deserts, while others in wetter climates developed different specializations. The seeds of diversity were being sown, but these geological shifts weren't gentle. Evidence from layers of basalt flows, massive volcanic eruptions that blanketed whole regions, reveals that pulses of activity sent carbon dioxide surging into the atmosphere. The result? Global warming events that could swing temperatures by several degrees, stressing ecosystems already stretched thin. Plants withered in arid regions, pushing herbivores to migrate or die. Predators followed, triggering constant reshuffling of survival strategies. And then came the storms. As warm oceans built up energy, they unleashed monsoonal rains in some regions while leaving others in drought. Imagine a world where one season you're surrounded by endless greenery, and the next, bone-dry plains stretch for hundreds of miles. For early dinosaurs, adaptability wasn't optional, it was a matter of life and death. Fossilized trackways from this time tell a vivid story. Herds of prosauropods moved in organized lines, suggesting that cooperation and migration became strategies to endure unstable climates. Predatory dinosaurs left traces alongside them, shadowing these herds, waiting for weakness. Even insects, amphibians, and small mammals were locked into this turbulent rhythm, rising and falling with each environmental pulse. It's tempting to see this as chaos, but in reality it was a crucible. By forcing constant adaptation, Earth was forging resilience into the DNA of dinosaurs. Their ability to exploit niches, to grow larger, faster and more efficient, was sharpened in this era of upheaval. This is what made them so unstoppable later. They weren't just lucky survivors of one extinction. They were products of a world that demanded innovation every single generation. In many ways, it wasn't just dinosaurs evolving. It was Earth itself training them for dominance. As the Triassic bled into the Jurassic, the story of dinosaurs took its most dramatic turn yet. From the chaos of extinctions and climate upheavals emerged a new chapter, the rise of the true giants. If the early dinosaur world was about experimentation, slender hunters, nimble herbivores, and small-bodied opportunists, the Jurassic world was about scale. Size became survival, and it changed everything. The supercontinent Pangaea had finally fractured enough to create vast inland seas and new coastlines. These waterways acted like natural highways, moving moisture across the land, stabilizing climates and allowing plants to grow in abundance. Ferns, conifers and cycads spread into forests that could feed animals of unprecedented size, and nature answered that invitation. Enter the sauropods, creatures like Brachiosaurus and Diplodocus that stretched over 80 feet long and weighed more than 50 tons. These weren't just animals, they were ecosystems on legs. A single adult sauropod needed a forest's worth of leaves each day to survive. Yet their long necks, column-like legs and air-filled bones weren't clumsy adaptations. They were precision-engineered solutions to life at an immense scale. Their skeletons reveal air sacs connected to lungs, a respiratory system so efficient it allowed these giants to grow to sizes no land mammal has ever reached. But the rise of giants wasn't just about herbivores. Predators evolved to match them. The Jurassic saw the emergence of apex hunters like Allosaurus, whose jaws and claws could take down prey many times its size. These predators weren't solitary. Fossil evidence suggests coordinated attacks, a terrifying glimpse of strategy in creatures often thought of as mere brutes. Imagine entire packs shadowing a herd of sauropods, waiting for the weak, the young, or the old to fall behind. The fossil record paints this period as a balance between abundance and danger. Footprints show sauropod herds moving together across mudflats, while predator tracks weave in between, always lurking. It was a world where scale dictated survival, and every evolutionary advantage mattered. But size wasn't the only story. With oceans expanding and climates stabilizing, ecosystems became more complex. Dinosaurs were no longer just adapting to survive. They were mastering their environments. From soaring pterosaurs filling the skies to marine reptiles ruling the seas, this was the dawn of ecosystems that would dominate Earth for over 100 million years. The giants of the Jurassic didn't just represent evolution's boldest experiment in size. They were the outcome of every storm, every extinction, every tectonic shift that had come before. Earth had tested life with fire and upheaval, and now in the Jurassic it rewarded resilience with abundance. If the Jurassic was the age of giants on land, it was also the first era when Earth's skies truly filled with life. Until this point, flight had been the domain of insects, buzzing dragonflies with wingspans as wide as a hawk's, but now vertebrates joined the sky. For the first time, animals with backbones lifted from the ground and learned to ride the winds. The pterosaurs were the pioneers. Evolving from small, lightly built reptiles, they developed wings of skin stretched over elongated fingers, a design very different from the feathered flight that would come later. Some were no larger than sparrows, skimming across lakes to snap up fish. Others, like Dimorphodon, had wingspans of 4 feet and sharp teeth built for catching prey on the move. But these were just the beginning. By the late Jurassic, species like Pterodaustro and Pteranodon would master the skies with wingspans of over 20 feet. The arrival of aerial predators and scavengers changed ecosystems in profound ways. Small dinosaurs and mammals that once had no reason to glance upwards suddenly had to watch the skies. For insects, which had ruled unchallenged for hundreds of millions of years, the air was no longer safe. The food chain had acquired a new dimension. At the same time, another quiet revolution was unfolding, one that would eventually reshape the entire planet. Among small, feathered dinosaurs, some species began to experiment with gliding and primitive flapping flight. Fossils like Archaeopteryx, discovered in Bavarian limestone, reveal a mosaic of traits, teeth and claws like a reptile, but feathers designed for flight like a bird. Was Archaeopteryx the first bird, or just another feathered dinosaur testing the possibilities of the sky? Paleontologists still debate that question, but one thing is clear. Flight had begun its long evolutionary journey, and it would never be reversed. The skies were not empty backdrops to the drama on land. They were theatres of innovation. To fly was to see more, hunt differently, escape predators in a new way, and colonize niches no land-bound animal could reach. From cliffs to coastlines, forests to open seas, pterosaurs and early birds expanded life's reach into a third dimension. And this expansion wasn't limited to predators. Plant life benefited too. With flyers spreading pollen and seeds, forests grew more diverse, ecosystems more interconnected. The skies became highways for genetic exchange, subtly preparing the Earth for ecosystems that resemble those we see today. The Jurassic wasn't just the age of giants, it was the moment when Earth itself became multi-layered, with drama playing out not only on the ground and in the sea, but also in the open air. And once the skies came alive, Earth's evolutionary story became something richer, faster, and far more unpredictable. If the skies of the Jurassic were alive with wings, the oceans were no less dramatic. Beneath the waves, the seas were ruled by creatures that made even the largest dinosaurs look modest. Imagine slipping below the surface of a Jurassic shoreline. The water is warm, rich with plankton and brimming with life at scales hard to comprehend. Here, colossal ichthyosaurs, dolphin-shaped reptiles stretching more than 20 meters in length, cut through the water like submarines.
These giants weren't fish, and they weren't quite dinosaurs either. They were reptiles fully adapted to the sea, with enormous eyes, some the size of dinner plates, allowing them to see in the deep, dim waters where their prey often fled. Their bodies were built for speed, capable of bursts over 30 miles per hour, making them some of the fastest hunters of their time. But ichthyosaurs were not alone. Alongside them swam plesiosaurs with long necks that could snake through schools of fish. Their anatomy was bizarre. Imagine a sea lion with a giraffe's neck. Yet it worked. That elongated neck allowed them to dart their heads into tight swarms of prey, snapping up fish and ammonites with a sudden strike. Paleontologists still debate whether these necks were used like stealthy spears or sweeping nets, but either way, they gave plesiosaurs a hunting edge. And then there were the pliosaurs, the heavyweights of the seas, with skulls longer than a grown man and jaws lined with teeth like railroad spikes. They were the apex predators of these oceans. Fossils of Kronosaurus show an animal so powerful it could bite through the shell of giant turtles or even prey on other marine reptiles. Their bite force may have rivaled or exceeded that of Tyrannosaurus rex, except it was deployed underwater in a silent and alien world. The Jurassic seas weren't just about giants, though. They teemed with ammonites, coiled shell relatives of squid and octopuses. These creatures were both prey and survivors, adapting to countless predators across millions of years. Their shells, now turned to stone, serve as one of the most abundant fossils of the Jurassic, spiraling reminders of a lost ocean ecosystem. Picture it. Above the waves, pterosaurs wheeled through the skies. On the land, sauropods shook the forests, and beneath the water, shadows of ichthyosaurs, plesiosaurs, and pliosaurs glided in silence, their vast silhouettes drifting like leviathans. The earth, in every realm, land, sea, and sky, was alive with giants, and yet, even in this world of abundance, changes were brewing. Ocean currents shifted, ecosystems evolved, and some of these giants, despite their dominance, were already writing the first lines of their extinction story. The Jurassic oceans weren't just vast theatres of reptilian giants, they were shaped by forces far larger, slower, and more relentless. The planet's climate and shifting seas. To understand why these creatures thrived where they did, we have to zoom out, away from the ichthyosaurs and pliosaurs, and look at Earth as a whole. During the Jurassic, the climate was warm, far warmer than today. There were no polar ice caps, sea levels were higher, and shallow seas flooded deep into the continents. Picture vast stretches of coastlines, shallow lagoons and inland seas, fertile zones where life flourished in staggering diversity. These shallow waters became nurseries for ammonites, fish and marine reptiles, while also feeding coral reefs that stretched across thousands of kilometers. The driving engine of all this was the supercontinent Pangaea, slowly tearing apart. As rifts split landmasses, new oceans were born. The Atlantic, just beginning its life, was a narrow seaway, connecting ecosystems in ways that would have seemed impossible when all the continents were locked together. Those rifts also changed ocean currents. Instead of a single vast inland sea, circulation patterns began to divide, creating regional climates and isolating species. Along the coastlines, the story was equally dramatic. River deltas poured nutrients into the seas, supporting plankton blooms that fed whole food chains. Fossil evidence suggests that fish diversity skyrocketed during this time, partly because new habitats kept forming as coastlines shifted. Where the seas met the land, you might have seen forests of conifers and cycads leaning toward the beaches, while giant ferns and horsetails crowded the marshlands. These lush fringes provided nesting grounds for pterosaurs, and in some regions, hunting grounds for smaller dinosaurs that waded into tidal flats. The climate, warm and stable, acted like an incubator. Reptiles could grow larger, ecosystems could expand farther,
and even evolutionary experiments, like plesiosaurs with necks of 20 feet, had the time and space to succeed. But stability came with risk. When the climate changed, through volcanic eruptions, shifting CO2 levels, or changing sea circulation, the ecosystems that had become so finely tuned could stumble. And some did. Think of it as a delicate balance. Giant reptiles ruled the seas, but their kingdom was built on the invisible scaffolding of currents, temperatures, and nutrients. Change the scaffolding, and everything else trembled. And as Earth's plates continued to move, those changes became more frequent. The Jurassic world was never still. Even its warmth and abundance carried the seeds of disruption. If the warmth of the Jurassic world made it feel like a paradise, it was a paradise built on restless foundations. Beneath the calm waves where ichthyosaurs hunted and ammonites drifted, Earth itself was tearing open. Volcanic forces and shifting tectonic plates were rewriting the planet's surface, and with it, the story of life. The breakup of Pangaea was not a quiet affair. As the supercontinent fractured, enormous rift valleys split the land. Those fractures became conduits for magma, spilling out vast sheets of lava. In some places, these eruptions lasted not for years, but for hundreds of thousands of years, releasing unimaginable volumes of gas into the atmosphere. Carbon dioxide levels rose, trapping more heat and amplifying the greenhouse world that reptiles called home. Underwater, the picture was just as dramatic. Hydrothermal vents spewed superheated water rich in minerals. Around them, strange ecosystems may have flourished, powered not by sunlight, but by chemistry. These vent communities, ancient analogues of the ones we still see today near mid-ocean ridges, may have provided both refuge and opportunity for organisms during times of stress. Fossils from Jurassic black shales hint at pulses of low oxygen conditions in the seas, likely triggered by volcanic gas and nutrient influxes. When oxygen levels dropped, entire regions of the ocean floor turned deadly for most life, creating ecological bottlenecks. But disruption also meant innovation. As old ecosystems collapsed, new ones took their place. Volcanic ash enriched soils on land, feeding forests that grew thicker and faster. Coastal lagoons, periodically stressed by eruptions, forced marine reptiles and fish into new niches, driving evolutionary change. It was a world constantly in flux, and that flux kept life adaptable. Imagine standing at the edge of a rift valley in the late Jurassic. To one side, dense forests of conifers. To the other, a glowing horizon where fountains of lava painted the sky red. In the distance, shallow seas boiled with life, while the land itself cracked and shifted beneath your feet. For creatures of the time, this was not a rare spectacle. It was the background rhythm of existence. The story of life in the Jurassic wasn't just about biology. It was geology, chemistry, and climate braided together. Every shift in a fault line, every volcanic eruption, every surge of gases into the atmosphere rewrote the rules of survival. And as these forces shaped Earth, they also laid the foundations for the next great act in the planet's evolutionary theatre, one where continents, climates, and creatures would transform once again. The volcanic upheavals of the Jurassic didn't just reshape the land, they rewrote the seas. When continents rifted apart, new coastlines stretched for thousands of miles, and the shallow continental shelves they created became some of the richest habitats Earth had ever known. These margins, bathed in warm sunlight and fed by nutrients from rivers and volcanic ash, were perfect cradles for explosive biodiversity. The opening of the Atlantic Ocean was one of the most profound changes. At first, it was no more than a narrow rift filled with brackish lagoons, but as Pangaea's pieces drifted further apart, it widened into a true ocean. With that came new circulation patterns. Currents carried warm water poleward, spreading the Jurassic greenhouse climate even farther. The tropics expanded, and ecosystems followed. But the new seas were not without hazards. Episodes of low oxygen, triggered by volcanism and changing currents, created vast, dead zones in some parts of the oceans. In these places, sediments record an eerie picture. Rich fossil beds where entire layers of ammonites, bivalves, and planktonal organisms perished together, entombed in black shale. For marine reptiles, the ichthyosaurs, plesiosaurs, and pliosaurs, survival meant moving constantly, chasing oxygen-rich waters and adapting to new prey distributions. The ecological pressure created winners and losers. Ammonites, masters of adaptation, diversified into a dizzying array of shell shapes, each suited to a slightly different niche. Plesiosaurs developed longer necks, turning into precision hunters of small fish in coastal lagoons. Meanwhile, pliosaurs went the opposite direction, becoming apex predators with skulls bigger than a human and jaws powerful enough to rival those of T-Rex millions of years later. For the fish themselves, evolution was just as rapid. Early teleosts, the group that would one day dominate modern oceans, began to outcompete older lineages with their more efficient jaws and faster swimming styles. Every reef and lagoon was a test bed for survival strategies that would echo into the modern age. To imagine this world, picture a Jurassic shoreline, forests of tree ferns leaning over turquoise waters, ammonites drifting in the shallows, and, just beyond the surf, the shadow of a pliosaur cruising in search of its next meal. Life was abundant, but it was never safe. Every shift in currents, every fluctuation in oxygen levels, every pulse of volcanism reset the balance. The oceans of the Jurassic were laboratories of change. They didn't just respond to Earth's shifting geology, they amplified it, spreading new conditions across the globe. And with each wave and tide, they carried forward the story of survival into ever stranger forms. As the oceans of the Jurassic shifted and swelled, the land felt every ripple. Currents didn't just stir plankton, they drove rainfall patterns, nourished rivers, and carved new habitats on shore. The great rift valleys that split Pangaea weren't barren scars. They filled with lakes and wetlands, lush corridors where ecosystems flourished under the steady influence of the sea. This was no coincidence. Warm, shallow seas evaporated rapidly, pumping water vapor into the atmosphere. That moisture fell back onto the continents, drenching the rift zones in seasonal rains. Picture it. Monsoon-like storms sweeping over fern-filled valleys, while volcanic highlands towered on the horizon, glowing with eruptions. The result was a patchwork world. Wet forests along rifts, arid deserts farther inland, and vast floodplains connecting them like arteries. These environments became testing grounds for land-dwelling life. Dinosaurs, already diverse by the early Jurassic, expanded into these niches with remarkable speed. Small, agile theropods hunted along riverbanks, massive sauropods, their necks stretching like living cranes, grazed on cycads and conifers that thrived near water. Even early mammals, still tiny and nocturnal, scurried through undergrowth, nourished by the climate shifts of the seas. But the feedback loop ran deeper. As vegetation spread across floodplains, it stabilized soils, captured carbon, and altered the chemistry of the atmosphere. This, in turn, influenced the climate, which fed back into ocean circulation. Earth, even then, was a tightly connected system, each part responding to the other. What happened in the sea could reshape life on land in a matter of centuries. Fossil evidence paints vivid snapshots of this transition. In places like the Morrison Formation of North America, layers of sediment reveal alternating wet and dry cycles, ancient droughts followed by lush growth, each tied to global ocean currents. Bones of sauropods lie alongside fossilized fish and turtles, telling us these giants lived in worlds where rivers swelled, lakes evaporated, and seas left their mark even far inland. For the creatures themselves, adaptability was everything. Crocodile ancestors found opportunities in both water and land, lurking in river deltas. Amphibians clung on in shaded wetlands, and insects, dragonflies, beetles, and early pollinators, spread wherever plants and water allowed. The ecological explosion was as much about small players as it was about giants. The story of the Jurassic is often told through dinosaurs, but behind their rise was a deeper narrative. The pulse of the oceans, the rains they summoned, and the landscapes they reshaped. It was Earth, orchestrating its own symphony of change, pulling sea and land into a single dance of survival. It might sound strange, but the oceans didn't just fill the world with water. They built mountains too. Every time tectonic plates shifted beneath the sea floor, oceans pressed their weight against continents, folding rock upward like paper being crumpled. This is how entire mountain ranges, including the ancestors of today's Rockies and the first stirrings of the Himalayas, began their rise. The secret lies in subduction, where one plate carrying seafloor is dragged under another. As that ancient ocean floor plunged into the Earth's mantle, it carried water with it. That water lowered the melting point of rock deep underground, fueling volcanic chains. It's why so many great mountain ranges also carry scars of volcanoes. Oceans, quite literally, sculpted the skyline of Earth. And this wasn't just geology for its own sake. The creation of mountains reshaped climate. As peaks rose higher, they disrupted wind patterns, casting shadows that created new deserts, while valleys on the windward sides grew lush with rainforests. Ocean-driven mountains changed the way rain fell, the way rivers carved their paths, and even how species migrated. Imagine early mammals and reptiles adapting to entirely new environments, forced to climb, burrow, or migrate as landscapes changed. These mountains were not random accidents. They were born from oceans pulling the strings of geology. And, in a way, oceans set the stage for the world we know now. Without them, there would be no Himalayas piercing the sky, no Andes catching the Pacific winds, no cycles of erosion feeding nutrients back to the seas. Oceans made the land, broke the land, and lifted it skyward. But mountains were only half the story. The oceans themselves became Earth's first great climate machines. Covering most of the planet, they absorbed sunlight, stored heat, and carried it across the globe like conveyor belts of energy. Ancient currents transported warmth from the equator toward the poles, while dragging cold water back toward the tropics. This circulation did something extraordinary. It kept Earth habitable. Without oceans distributing energy, large parts of the planet would have swung between extremes, blistering deserts at the equator and frozen wastelands at the poles. Instead, oceans softened the climate, creating a more stable world where life could spread and diversify. Oceans also breathed with the atmosphere. They absorbed carbon dioxide during some eras and released it in others, driving long cycles of warming and cooling. Scientists can still trace these changes today in the chemical fingerprints of ancient rocks and the shells of long-extinct marine organisms. Every rise and fall in ocean chemistry left a story written in stone. And here's the hook. Sometimes those changes were catastrophic. Ocean currents could stall, carbon could spike, and Earth would plunge into hothouse periods or ice ages. The deserts we know today, the Sahara, the Gobi, even the dry heart of Australia, were partly shaped by ocean-driven climate shifts millions of years ago. Once again, deserts and seas weren't opposites. They were partners in shaping Earth's balance between life and extinction. Imagine standing on Earth during one of its most dramatic rearrangements, when supercontinents fractured and ancient seas flooded deserts. Animals were forced into a game of survival. Whole populations found themselves stranded on new coastlines, while others suddenly had to adapt to wetter, colder, or hotter worlds. For paleontologists, this is one of the most fascinating puzzles. The fossil record shows clear evidence of mass migrations, sudden disappearances, and surprising reappearances. For example, species that once thrived in dry inland basins were suddenly surrounded by shallow seas. Many died out, but a few adapted. Reptiles evolved new salt-tolerant physiologies, while early amphibians used the changing waterways to expand their range. And here's where it gets really intriguing. Sometimes animals vanished from one continent only to re-emerge millions of years later on another. How? Because drifting land masses created new land bridges and fresh migration routes. It was as if Earth's geography itself was shuffling the deck of life, dealing out survival chances in unexpected patterns. This faunal shuffle is not just random noise, it's a recurring pattern. Every breakup of a supercontinent, every flooding of a desert, rewrote the evolutionary story. The losers were often the highly specialized creatures. The winners were the flexible, the adaptable, the ones that could eat almost anything and live almost anywhere. That rule still echoes today. It's why rats, crows, and humans thrive where other species struggle. So when we say Earth's shifting crust shaped life, it's not just about mountains and oceans. It's about forcing living things into brand new arenas where only those willing to change could survive. And the fossil record reads like a set of clues, showing us exactly which animals bent with the changes and which snapped. And then, something extraordinary happened. Those endless deserts, once so dry and lifeless, began to drown. Vast inland basins filled with water as global sea levels rose, swallowing dunes and salt flats beneath shallow tropical seas. Imagine the Sahara not as a desert, but as a warm inland ocean buzzing with early marine life. The geological fingerprints are undeniable. In places like what is now North Africa, thick layers of limestone and fossilized coral reveal that entire regions once sat under warm, shallow waters. Even deserts like the American Southwest carry traces of ancient seashells, proof that they too were submerged. These were not brief floods, they lasted millions of years, reshaping whole ecosystems. For animals, this was both disaster and opportunity. Desert reptiles and amphibians lost their arid strongholds, but marine species flourished. Trilobites, brachiopods, and early fishes suddenly had new playgrounds to expand into. Entire evolutionary experiments took place in these temporary oceans. Some species adapted so well that when the seas later retreated, their descendants followed rivers and lakes inland, spreading across the continents. But here's the most astonishing part. These drowned deserts may have acted as evolutionary laboratories. With isolated pockets of water cut off from the wider ocean, species were forced into rapid adaptation. Fossils show bursts of diversification, unique forms of fish, mollusks and early crustaceans that appear in no other parts of the world. It was as if Earth itself ran an experiment. What happens when you give life a flooded desert and a few million years to adapt? The result wasn't just local oddities. It changed the trajectory of ecosystems for ages to come. When the waters eventually retreated, many of those creatures were stranded, forced to reinvent themselves on land or vanish entirely. In a way, drowned deserts created both stepping stones and dead ends in the evolutionary story. But these drowned deserts didn't just hold seas, they birthed kingdoms. In those shallow, sunlit waters, life began constructing vast reef systems, unlike anything we see today. Picture a barren desert swallowed by turquoise waves, now crowned with towers of coral-like organisms, stromatoporoids, tabulate corals, and sponges, building intricate fortresses of stone. These reefs became epicenters of life. Swarms of trilobites crawled across the sea floor, jawless fishes darted through the water, and early cephalopods patrolled as apex predators. Fossil evidence shows that these reefs stretched for hundreds of kilometers, forming belts of biodiversity that rivaled the rainforests of today. And here's the twist. Reefs in drowned deserts weren't permanent. They rose and fell with sea levels, collapsing when waters retreated, only to be reborn when the deserts drowned again. That cycle of creation and destruction turned these reef kingdoms into evolutionary crucibles. Every collapse forced survivors to adapt, diversify, or vanish, and every rebirth seeded new experiments in form and function. Some scientists believe that these shifting reef systems played a direct role in shaping marine ecosystems as we know them. Predator-prey arms races accelerated, shell designs became tougher, and fish learned to move faster. The world's first large-scale ecological arms races may have started here, in seas that existed where deserts once lay. What's remarkable is how much of that legacy endures. The very limestone cliffs we see in places like Morocco or the American Midwest today are fossilized remnants of these ancient reef cities. Every ripple and fossil imprint tells us that deserts are not always endings. Sometimes they're the foundation for new worlds. And just when these new reef systems seemed invincible, something unexpected began to unfold. The very seas that nurtured them were restless. Ocean chemistry was never stable in deep time. It shifted like a living machine, sometimes favoring life, sometimes threatening it. During the Silurian, the oceans grew rich in calcium carbonate, perfect for corals and stromatoporoids, those sponge-like reef builders. They flourished, building massive reef belts stretching across entire coastlines, ecosystems so large they could be seen from orbit if satellites had existed. But with that abundance came vulnerability. Too much carbonate, too fast, could tip the balance. Reefs became overgrown, brittle, and highly sensitive to even minor environmental changes. Add to this the fluctuations of global sea levels. Every glacial advance lowered the oceans, exposing reefs to the air, killing entire systems in a geological instant. When glaciers melted, seas returned, but the regrown reefs were never quite the same. Each collapse left scars in the fossil record, sharp breaks between thriving life and sudden silence. And life adapted again. Some species specialized in surviving stress, trilobites that burrowed into sediment, fish that hugged the edges of reefs where water stayed cooler. Others vanished completely, never to return. The story here is not just of growth, but of fragility. These early reef systems, born from drowned deserts, were both a triumph and a warning. Complex ecosystems could dominate, but they could also be dismantled almost overnight. It's a pattern we'll see again and again through Earth's history. And this brings us to a crucial turning point, because the stage was being set for one of the greatest transformations life had ever attempted. Something that would forever change the balance between ocean and land. From fragile reefs, the story of life takes a bold step, literally. Around 430 million years ago, some creatures began to explore the shoreline. It wasn't a dramatic leap onto land all at once, but a cautious testing of boundaries, an experiment driven by survival. Tidal pools and coastal shallows became laboratories for innovation. Algae clung to wet rocks, spreading into mats that trapped moisture. Primitive plants, small moss-like pioneers, extended tiny structures above water, capturing sunlight more efficiently. These green patches stabilized soils, turning bare mudflats into miniature oases. Animals soon followed. The first were not large fish or reptiles, but tiny arthropods, scorpion-like eurypterids, millipede ancestors, and early relatives of insects. They crept onto damp shorelines in search of food and safety, retreating to the water when danger loomed. Fossilized trackways from this time capture their cautious experiments, delicate trails across ancient sands, preserved like whispers of ambition. Why risk land at all? The answer lies in competition. In the ocean, predators were everywhere. On land, the playing field was nearly empty. For a small creature willing to risk drying out, the rewards were enormous. Sunlight, fresh plant matter, and safety from hungry jaws. Evolution began to favor those who could breathe air more effectively, resist desiccation, and support their bodies without buoyant water. This shift was not a revolution, but a creeping tide of adaptation. Step by step, life claimed a new frontier. And though these early pioneers were fragile, they set in motion a chain of events that would reshape the planet forever. Because once life gained a foothold on land, there was no turning back. The balance of Earth's ecosystems would never be the same again. The first steps onto land had been taken, but Earth's surface still looked barren. Mudflats, low mats of algae, and scattered moss-like plants clinging to damp soil. Then came one of the most transformative events in planetary history, the rise of vascular plants. Unlike their primitive cousins, these plants developed internal tubes, xylem and phloem, that carried water and nutrients upward. This single adaptation allowed them to grow taller, pushing higher into the air to capture sunlight. Imagine landscapes that had once been flat and colourless, suddenly sprouting knee-high groves of primitive club mosses, horsetail ancestors, and spiky ferns. These early forests were nothing like the towering woodlands we know today. They were dense thickets of simple stems, no flowers, no leaves in the modern sense, just green spires rising above the ground. Yet they changed everything. For the first time, shade existed on Earth's land surface. Roots dug deeper, breaking down rock and creating true soil. Rivers shifted course as plant roots anchored sediment, altering landscapes in ways unseen for billions of years. But perhaps the most profound change was invisible. As plants spread, photosynthesis accelerated. Vast amounts of carbon dioxide were drawn from the air, and oxygen flooded the atmosphere. This chemical rebalancing reshaped Earth's climate, cooling temperatures and paving the way for entirely new ecosystems. And in those shaded thickets, hiding among the stems and damp litter, the first true terrestrial animals began to thrive. Arthropods multiplied, experimenting with new niches. Predators followed prey, and the ancient arms race moved from the oceans onto land. The stage was set. Life was no longer tied to the sea. The world was about to witness an explosion of ecological innovation that would turn Earth into something entirely new. While plants reshaped the air and land, another silent revolution was stirring in the shallows. For millions of years, fish had ruled the seas. They evolved jaws, strong fins, and even primitive lungs. But some faced environments where water levels fluctuated. Estuaries, tidal flats, and swampy shallows that could dry up in scorching heat. Survival here required innovation. From these pressures came an extraordinary leap, the first vertebrates to step onto land. These were not the sleek reptiles of later ages, but lobe-finned fish like Tiktaalik and Acanthostaga. They possessed sturdy, muscular fins with bones that eerily resembled arms and legs. They could push their bodies along mudbanks, gulp air with primitive lungs, and retreat back to water when threatened. Imagine one of these creatures, half fish, half amphibian, dragging itself from a weedy pool into a damp fern thicket. Each awkward movement was a test run for the entire future of land animals. Without these tentative crawls, there would be no amphibians, no reptiles, no dinosaurs, and no mammals. The ecological payoff was immense. On land, there were no vertebrate predators, only insects, millipedes, and scuttling arthropods. The first amphibians became pioneers in a world filled with untouched food sources and no rivals. For a brief moment, the planet belonged to them. This was more than a new chapter in life's story. It was the opening of an entirely new book. Evolution had discovered a way to colonize the driest, most hostile frontier yet, the continents themselves. And as these amphibian-like pioneers gained their footing, evolution prepared its next bold experiment. Creatures that would one day sever their dependence on water entirely. The amphibians may have been the first to explore land, but they carried a weakness with them: their ties to water. Their eggs were soft and jelly-like, laid in ponds and swamps. Without a constant source of water, their offspring could not survive. It was as if every generation had to retreat to the same ancient cradle. But then came one of the most revolutionary innovations in the history of life: the amniotic egg. Within its tough, leathery shell, life could unfold in safety, protected from drying out. Inside were compartments that stored food, managed waste, and kept the embryo in a miniature ocean of fluid. With this single adaptation, vertebrates broke free from water's leash. These early reptiles were not yet dinosaurs, but they carried the blueprint for everything that would follow. They were small, scaly, and cautious, spreading across the new forests and floodplains of the late Paleozoic. Some remained insect eaters, others began experimenting with plant-based diets, paving the way for the enormous herbivores that would later dominate Earth. Imagine the scene: damp carboniferous swamps filled with giant dragonflies and towering ferns, while among the shadows the first reptiles scurry over rotting logs. They look unremarkable, yet their eggs allow them to conquer uplands, deserts, and landscapes no amphibian could ever reach. This was a quiet revolution. No dramatic asteroid, no sudden extinction, just a slow, relentless expansion powered by the egg. And from this modest beginning would arise entire dynasties, creatures that would one day take command of the skies, the oceans, and the land. The stage was now set for the Age of Giants, but first, Earth itself had a surprise in store. A catastrophic upheaval that would nearly erase these pioneers before their story even began. The egg was not just a survival strategy, it was a declaration of independence from the swamps. With the amniotic egg, reptiles no longer needed to return to water to reproduce. This innovation opened an entirely new frontier. Dry forests, uplands, even arid plains. Suddenly, creatures that once gasped for air in stagnant ponds could stride confidently across sun-baked landscapes. These first reptiles were small, lizard-like beings, hugging the ground, their scales shimmering in the Paleozoic sun. They were not yet the masters of their world, but they were free from the tether of water. Unlike their amphibian cousins, their skin resisted drying. Their eggs carried their own tiny, aquatic world, and their lungs were more efficient. Each hatchling was born ready for life on land. And this shift wasn't quiet. Forests that had echoed with the croaks of amphibians now carried the rustling sounds of reptiles moving through leaf litter, hunting insects, and laying their eggs in secret places. It was a subtle revolution, one that transformed ecosystems. But with freedom came new pressures. Dry uplands meant harsher climates, scarcer water, and new predators. To survive, reptiles had to innovate further. Some became armoured, some developed sharper teeth, and others learned to conserve energy in scorching heat. They were no longer just survivors. They were pioneers. From this quiet, almost unnoticed beginning, a lineage was forming that would one day dominate Earth's land masses. The amniotic egg had tilted the balance. The amphibian age was fading. The reptile age had just begun. And here's the question to carry us forward. If the egg unlocked land for reptiles, what would happen when they started to reshape their own bodies to master every corner of this planet? The first reptiles may have been small, but evolution rarely stays still. Within just a few million years, these humble, lizard-like creatures branched into astonishingly different forms. Some stayed small and nimble, scuttling in the undergrowth, their sharp teeth perfect for snapping up insects. Others grew larger, experimenting with body shapes that had never existed before. This was the Great Reptilian Divergence, a branching of lineages that would set the stage for all the reptilian dynasties to come. Some evolved into the ancestors of modern turtles, with ribs broadening into protective shields. Others experimented with lightweight skeletons and stronger legs, becoming swift predators that could chase down prey on land instead of lurking in water. And then there were the plant eaters. For the first time in history, vertebrates began adapting to graze on land plants, crushing tough ferns and seed-bearing shrubs with specialized teeth. It may sound simple, but this was revolutionary. Up until then, most large land animals had been carnivores or insectivores. Plant-eating reptiles carved out a new ecological role, reshaping landscapes and paving the way for future herbivorous giants. The Earth itself seemed to reward this adaptability. Expanding forests provided food and shelter, while drier uplands demanded resilience. Every niche, every environment, invited a new evolutionary experiment, from tiny insect-hunting scurriers to the first bulky herbivores. Reptiles were no longer just survivors. They were beginning to dominate. But this was only the opening act. The real drama would come when these early lineages diverged even further, setting into motion the long evolutionary story that would eventually give rise to dinosaurs, crocodiles, turtles, and even the ancestors of birds. So here's the hook. The reptiles weren't just filling roles left behind by amphibians. They were rewriting the very rules of life on land. The question now is, what form of reptile would push evolution to its most daring extremes? From the outside, these early reptiles may have all looked somewhat alike, scaled, sprawling, low to the ground. But under the skin, evolution was splitting them into two very different dynasties. On one path were the sauropsids, the lineage that would eventually give rise to lizards, crocodiles, dinosaurs, and birds. Their skulls developed openings behind the eyes, extra space for muscle attachment that gave them stronger, more efficient bites. A small change in bone structure, but one that would echo through hundreds of millions of years. On the other path were the synapsids, a group that looked reptilian but would ultimately evolve into something entirely new, the ancestors of mammals. Their skulls bore a single opening behind the eyes, also for stronger jaws, but with a different architecture. Over time, synapsids began developing faster metabolisms, sharper teeth with distinct shapes, and a more active lifestyle. They weren't mammals yet, but they were on that road. This split, sauropsid versus synapsid, was one of the most important divergences in evolutionary history. It's the reason we humans, sitting here today, don't descend from dinosaurs or crocodiles. Instead, we're distant cousins of those first synapsid reptiles. Imagine the late Carboniferous world. Dense forests, sprawling swamps, insects buzzing through the air. Among the underbrush, two similar-looking creatures scurry past each other. At the time, no one, if anyone had been watching, could have guessed that one lineage would dominate the skies as pterosaurs and birds, while the other would one day give rise to mammals capable of building cities and asking cosmic questions. And here's the twist. At first, the sauropsids seemed to have the upper hand, branching out into countless forms. But the synapsids, our own lineage, quietly held on, laying the groundwork for their eventual comeback after Earth's greatest catastrophe. This moment in history was more than just a split in anatomy. It was the laying down of two evolutionary destinies, parallel paths that would shape everything about life on Earth for the next 300 million years. The real question is, in a world dominated by giant reptiles, how did the small, often overlooked synapsids manage to survive long enough to eventually take over? So, how did the synapsids, our unlikely ancestors, survive in a world where reptiles were multiplying and spreading across nearly every environment? The answer lies in adaptability. Early synapsids weren't the biggest, nor the most fearsome, but they were innovators. Their jaws and teeth began to show specialization. Unlike most reptiles, whose teeth were often uniform, synapsids developed different types: sharp canines for biting, flat molars for grinding. That meant they could eat a wider variety of food, from insects and small prey to tough plant matter. In a competitive world, this flexibility was everything. But it wasn't just teeth. Synapsids may also have been edging toward higher metabolisms, burning energy faster, and perhaps regulating their body temperatures in primitive ways. Some paleontologists even argue that whisker-like sensory hairs may have appeared earlier than we think, giving them an advantage in foraging at night or in cooler climates. Meanwhile, sauropsids, though incredibly successful, tended to specialize in particular niches. If the environment shifted suddenly, those specialists were more vulnerable. Synapsids, on the other hand, were building resilience into their biology. They weren't dominating yet, but they were quietly playing the long game. Picture it: dense carboniferous forests, giant dragonflies with wingspans nearly as wide as a hawk's, amphibians lumbering by the swamp waters, and among them, small, agile synapsids scurrying under the cover of night. They were rarely the top predator, but they were survivors, finding ways to thrive in the margins. This is the part of Earth's story that often goes overlooked. Evolution isn't always about who dominates today, but who adapts to tomorrow. And the synapsids were unknowingly preparing for a future no one else could see coming. A future where disaster would sweep the stage clean, giving them their chance. Because soon, Earth was about to face one of the most dramatic upheavals in its history. And then, catastrophe struck. Roughly 252 million years ago, at the end of the Permian period, the world entered what scientists call the Great Dying. It was the largest mass extinction event in Earth's history. Imagine it. Over 90% of all marine life wiped out, and about 70% of land species gone. Forests collapsed. The very foundation of ecosystems disintegrated. The cause? A perfect storm of disasters. Gigantic volcanic eruptions in what is now Siberia poured out lava the size of continents, releasing staggering amounts of greenhouse gases. The oceans turned acidic, oxygen levels plummeted, and temperatures soared in some regions while freezing in others. It was chaos. Climate collapse on a scale no living thing had ever faced before. For the synapsids, it was an unimaginable trial. The once thriving lineages of mammal-like reptiles were devastated. Many groups perished entirely. Yet, in this crucible, a handful of survivors endured. Among them were the therapsids, an advanced branch of synapsids that had already begun experimenting with more efficient breathing systems, stronger limb structures, and possibly even the first hints of warm-bloodedness. Picture it again. The land is barren, skies hazy with volcanic ash, rivers poisoned, prey scarce. In this wasteland, size and strength mattered less than endurance, adaptability, and innovation. The reptilian rulers, many of them giant, specialized predators, simply couldn't adjust quickly enough. But synapsids, already dabbling in traits that would later define mammals, had just enough resilience to cling on. It's here that we glimpse one of evolution's harshest truths. Survival is not about perfection. It's about persistence. And through persistence, the ancestors of mammals managed to endure Earth's darkest hour. This was their turning point. The extinction didn't just erase competitors, it cleared the stage. What had once been a quiet background role for synapsids was about to shift into something far greater. Because out of the ashes of the Great Dying, a new evolutionary story would begin. One that slowly, step by step, leads directly to us. When the dust finally began to settle, the Earth was no longer the same planet. The Permian extinction had rewritten the rules of life. Whole lineages that had once dominated, giant amphibians, many reptilian predators, entire forests, were gone. What remained was a scarred, almost alien world. But in that emptiness lay opportunity. The early therapsids, battered but not broken, began to adapt to this new landscape. These survivors weren't the largest or the fiercest, but they carried traits that gave them an edge in this unstable world. Their bodies were becoming more efficient. Evidence from fossilized rib cages suggests improved breathing mechanics, lungs that could draw in oxygen more effectively, a life-saving adaptation when the atmosphere itself held less of it. Their teeth were becoming more specialized, incisors for snipping, canines for tearing, and molars for grinding. This shift hinted at flexible diets, a critical advantage when food was scarce and unpredictable. Some therapsids even show signs of hair-like structures, possibly for insulation. If true, this suggests that warm-bloodedness, the hallmark of modern mammals, was already being trialled in this time of crisis. Imagine that. Tiny, shrew-like creatures scurrying through the ruins of a broken world, their small bodies retaining heat while their reptilian cousins struggled. And with the apex predators largely gone, these modest creatures began to experiment with roles they'd never held before. They were no longer just background actors in the evolutionary play. They were moving towards center stage. What makes this moment extraordinary is how survival reshaped destiny. The extinction event could have ended the synapsid line completely. Instead, it pruned the tree of life, leaving behind only the most adaptable, the most inventive. Those survivors, unspectacular as they seemed, carried the seeds of mammals within them. So, from devastation came innovation. From scarcity came resilience. And quietly, in the shadow of catastrophe, the blueprint for every mammal, including us, was being written. And here's where the story takes an even stranger turn. Out of the battered survivors of the Permian extinction, a few therapsids began to evolve into something startlingly new. They didn't know it, of course, but in hindsight, they were sketching the very first draft of what would one day become mammals. Fossils from species like Thrinaxodon, a small burrowing creature, reveal something extraordinary. Its skull shows signs of a secondary palate, allowing it to breathe while chewing. That might sound trivial, but in evolutionary terms it's revolutionary. It meant a more efficient way to process food, more energy extracted from every meal, and an advantage in a resource-starved world. The bones of the inner ear tell a similar story. What were once jawbones in their reptilian ancestors were shrinking, shifting, and starting to specialize for hearing. Imagine being in a harsh, unstable environment where predators could rise from the shadows at any time. To hear better meant to live longer. That adaptation would eventually give mammals, and us, the acute hearing we rely on today. Even posture was shifting. Instead of the sprawling gait of reptiles, some of these early synapsids were drawing their legs more beneath their bodies. This small change offered more efficient movement, conserving energy and making them more agile hunters and foragers. In other words, nature was running experiments, tinkering with features that seemed minor in the moment, but would echo through deep time. Efficient breathing, better chewing, sharper hearing, warmer bodies, all were emerging in this strange chapter of Earth's history. And perhaps most remarkable of all, their behavior. Burrows discovered alongside Thrinaxodon fossils suggest they lived in family groups, possibly sharing shelter. Cooperation, another hallmark of mammals, may have begun here, in a desperate bid to endure a broken world. This was no longer just about surviving the extinction. It was about rewriting the rules of life itself. In these humble creatures, scarred by disaster yet quietly adapting, we can see the faint outlines of the future. Our future. But even with sharper hearing, stronger jaws and better posture, survival demanded something more radical. The climate after the Permian extinction was brutally unstable. Swings between scorching heat and bitter cold could kill off even the hardiest survivors. For reptiles, dependent on the sun's warmth, these extremes were a constant gamble. Some therapsids, however, began to change the game. Evidence suggests they were developing a more advanced metabolism, what we now call endothermy, or warm-bloodedness. Instead of waiting for the sun to heat their bodies, they generated their own warmth from within. This meant they could move at dawn, hunt in cooler nights, or endure chillier climates where reptiles struggled. The clues are hidden in their bones. Fossilized remains show fibrolamellar bone tissue, a sign of rapid growth. Reptiles grow in seasonal spurts, leaving ring-like patterns, but these proto-mammals grew more continuously, much like us. That growth pattern demanded higher energy intake, and it's one of the smoking guns pointing toward warm-blooded physiology. Their teeth tell the same story. While reptiles typically had simple, uniform teeth, these therapsids developed differentiation: incisors, canines, molars. Specialized teeth meant specialized diets, allowing them to process food more efficiently and fuel their energy-hungry bodies. Every bite became a step toward the mammalian way of life. And then there's the mystery of whiskers. Tiny pits found in fossil skulls hint that sensory hairs might have already been present, providing an evolutionary leap in awareness. Imagine being a small, vulnerable creature scuttling through burrows or underbrush. Those sensitive hairs could feel the faintest vibrations in the dark. With warmth in their blood and new tools to sense the world, these animals were not just survivors. They were innovators, finding ways to outlast the chaos around them. Each adaptation layered onto the next: hearing, chewing, posture, warm blood, stacking like evolutionary building blocks. In the ruins of a broken earth, the blueprint for mammals was no longer just an outline. It was being filled in, one innovation at a time. If warm blood gave these proto-mammals the power to roam beyond the sun's reach, it also opened a new frontier: the night. While most reptiles slowed or stopped altogether when the air cooled, therapsids with higher metabolisms could keep moving, keep hunting, keep surviving. But thriving in the darkness meant more than warmth. It meant seeing in low light, sensing movement in silence, and hearing the faintest rustle of prey. Fossil evidence suggests some therapsids began expanding the bony structures around their eyes and skulls. These changes point to enhanced vision and auditory sensitivity, traits that mammals would later perfect. Imagine a twilight world where reptiles retreated into sluggish stillness, yet small, warm-blooded hunters prowled on. Their whisker-like sensory hairs twitched at every vibration. Their sharp, differentiated teeth worked through insects, roots, or even small vertebrates. Night, once a place of danger, became a theatre where they quietly claimed dominance. This shift was profound. By becoming creatures of the night, they avoided direct competition with the sun-loving reptiles that still roamed the day. It was a clever evolutionary strategy. Divide the clock, divide survival. And it worked. While reptiles ruled the sunlit plains, these ancestors carved out an entirely new ecological niche under the stars. And here's the twist. This nocturnal tendency may have shaped mammalian evolution all the way to us. Our own reliance on acute hearing, the way our eyes adjust to dim light, even the fact that so many modern mammals, from mice to bats, are still nighttime specialists, all trace back to this ancient adaptation. By embracing the darkness, they weren't just surviving, they were innovating in secret, laying the groundwork for mammals to come. The Earth may have been recovering from devastation, but in the hush of night, the blueprint of the future was quietly being drafted. From prowling the night to crunching down prey, Their evolution left its clearest record not in their bones, but in their teeth. Because teeth fossilize so well, they are the most honest storytellers of deep time, and what those ancient jaws reveal is nothing short of revolutionary. Unlike reptiles, which mostly had rows of simple cone-shaped teeth, therapsids began experimenting. Some evolved sharper incisors at the front for cutting, strong canines for piercing, and flatter molars for grinding plant material. This shift, called differentiated dentition, was the first sign of what we now recognize in mammals: specialized teeth for specialized diets. Picture one of these creatures cracking open seeds under the cover of darkness, while its neighbor used dagger-like canines to tear into small prey. Each tooth pattern represented a unique evolutionary gamble, a way to survive in a world still reshaping itself after mass extinction. Even more intriguing is what these teeth hint at about metabolism. Chewing food more efficiently meant quicker digestion, which in turn fueled their higher energy lifestyles. A spiral of innovation. The better they ate, the more active they became. The more active they became, the more adaptations they needed to stay ahead. And this wasn't just a random quirk of survival, it was an arms race. Prey developed tougher shells and faster escape strategies. Predators developed sharper, stronger jaws to keep pace. The entire ecosystem was becoming more dynamic, less sluggish than the reptile-dominated landscapes before. When paleontologists study these ancient jaws today, they don't just see teeth. They see the very origins of mammals taking shape. Each ridge, cusp, and wear pattern is a breadcrumb trail leading from the shadows of the Permian into the rise of the mammalian dynasty. And here's the key. These early innovations in dentition gave mammals an edge that would eventually let them outlast the giants. Long before dinosaurs fell, the groundwork for resilience was already locked in enamel. But teeth were only the beginning. Hidden deeper in their skeletons was an even more startling clue, one that whispered of a metabolism unlike the reptiles they lived among. When paleontologists sliced open therapsid bones and studied their internal structure, they found something unexpected: fibrolamellar bone, a tissue that grows rapidly and is typical of animals with higher metabolisms. In other words, these creatures weren't lumbering, cold-blooded reptilian throwbacks. They were already experimenting with the energy systems that would one day define mammals. Think of it. While reptiles of the same age warmed themselves lazily under the sun, some therapsids may have been able to stay active in cooler conditions. Their bodies were shifting toward internal heat regulation, the earliest whispers of warm-bloodedness. Why did this matter? Because it opened new ecological doors. A predator that could stalk its prey at dusk or dawn without needing the sun to fuel its muscles had a massive advantage. Herbivores that could forage longer and endure temperature swings could colonize new environments. This wasn't just survival, it was expansion into ecological niches reptiles had never touched. Even their breathing systems may have been adapting. Studies of nasal cavities suggest some therapsids developed structures to moisten and warm incoming air, a feature crucial for sustaining higher metabolism. Pair that with the ability to chew food more effectively, and you begin to see a blueprint for endurance, agility, and resilience, the hallmarks of mammals. And yet, these transitions weren't perfect. Not all therapsids survived the gamble of evolution. Many branches died out, leaving only faint traces in the fossil record. But in the bones of those that endured, we see the spark that would carry forward into shrews, lions, and eventually, us. This was no longer a world of sluggish reptilian rhythms. It was a world where life was learning to burn hotter, move faster, and think sharper. If warm-blooded whispers hinted at change, then the shadows revealed the consequences. With the ability to generate more of their own heat, some therapsids were no longer bound to the daylight hours. They could hunt in the cool of evening, move under the stars, and carve out a new kind of ecological dominance. Imagine a Triassic plain at dusk. Giant reptiles grow sluggish as the temperature falls, their cold-blooded bodies stiffening with the night air. But from the underbrush emerges a different kind of predator, sleeker, sharper, alive with its own furnace of energy. These therapsids were pioneers of twilight, the first creatures to flirt with the rhythms of mammals to come. Their jaws tell the story. Evidence of powerful bite forces and differentiated teeth points to a varied diet. Some could crunch insects, others could shear flesh, and a few may have gnawed plants. The flexibility of their feeding strategies meant they weren't tied to a single food source, a trait that would prove vital in the unpredictable climates of the Triassic. And the eyes. Fossil evidence of enlarged eye sockets suggests some of these animals may have been adapted to low light conditions. If true, that means they weren't just surviving in the dark, they were thriving in it. This was evolution's experiment in versatility. Creatures that could move between day and night, heat and cold, predator and prey. They weren't yet mammals, but in their biology, we glimpsed the blueprint of the small, nocturnal survivors that would one day inherit the Earth after mass extinctions reshaped the planet. And it raises the question, what else were they developing that would eventually become essential to us? Because bones and teeth reveal more than diet or metabolism, they hold the secrets of senses, behavior, even the stirrings of intelligence. From the glow of warm blood and the hunt beneath the moonlight comes another innovation, one that seems almost too small to matter at first glance, but it would change everything. The rise of whiskers. Yes, whiskers. Not the cartoonish feature of a house cat, but a biological revolution. Fossil evidence from certain therapsids suggests that their snouts were lined with nerve-rich tissues, the kind that could anchor vibrissa, sensitive hairs capable of detecting the slightest vibrations in the environment. Why does this matter? Because in a world where survival often meant choosing between eating and being eaten, the ability to feel the world without seeing it was priceless. Under cover of night, when vision faltered and sound was deceptive, whiskers gave early mammal-like reptiles the edge. They could sense prey scuttling through the leaf litter, or predators approaching in silence. Think of it. While dinosaurs were beginning their march toward dominance in daylight, these therapsids were carving out their empire in darkness. Whiskers weren't just an adaptation for comfort, they were part of the toolkit of survival, laying the groundwork for the extraordinary sensory world mammals would later inherit. And more than that, whiskers hint at something even deeper, the evolution of touch and perception. Because to develop whiskers, you need nerves. You need a brain sophisticated enough to process tactile information, to interpret signals from the environment. It was a step toward complexity, toward awareness. So when you picture these creatures, don't just see squat, lizard-like animals of the Triassic. Picture pioneers of sensation, whiskers twitching in the dark, feeling the contours of a world that sight alone could never fully reveal. And that leads us to an even bigger question. If they were mastering the art of sensing the world in new ways, what about communicating it? Could these creatures already have been experimenting with the first building blocks of social behavior, the very spark of community that mammals would later perfect? Whiskers weren't just tools for hunting, they were also tools for connection. Imagine a group of small therapsids huddled together in the shadows, their whiskers brushing against one another, detecting the tiniest shifts in movement. In that moment, sensation became communication. This is where the story deepens. Fossilized burrows from the Triassic hint that some of these early mammal-like reptiles lived together, side by side. They weren't just solitary survivors, they were beginning to experiment with social living. And that is no small step, because once you live in a group, your evolutionary priorities shift. You need ways to cooperate, to recognize kin, to share warning signals against predators. Think of modern mammals, the alarm calls of meerkats, the social grooming of primates, the complex songs of whales. All of it begins with the recognition that survival isn't just an individual game. The seeds of that story may stretch all the way back to these Triassic pioneers. And what fueled it? Likely warmth. Warm-blooded bodies pressing together in underground shelters, conserving heat through the long, cool nights. A shared refuge meant more than comfort. It meant survival. And over countless generations, these patterns of gathering, of protecting one another, became encoded into biology. Here's where the progression is clear. From solitary reptiles to the whisper of society. From creatures defined by instinct to the beginnings of trust, memory, and even strategy. Each tiny behavioral shift echoed across deep time, preparing the way for the complex family structures and communities that define mammals today. So, as dinosaurs thundered across the earth above, these smaller, whisker-bearing creatures below were building something far quieter but far more enduring, the very architecture of social life. But here's the question we need to ask next. If society was forming in burrows and dark corners, what drove their survival when the skies themselves began to collapse? Just as these tiny proto-mammals were weaving the first threads of social life underground, the world above them was unraveling. The Triassic was not a time of stability. It was an era of fire, ash, and sudden change. Volcanoes split the land apart, belching greenhouse gases that turned skies murky red and oceans acidic. The supercontinent Pangaea groaned under tectonic stress, and ecosystems teetered on the edge. For the small, warm-blooded survivors, every night carried a choice: adapt or vanish. Above, towering archosaurs and the first true dinosaurs dominated the open plains. They grew larger, faster, and more terrifying with every generation, casting shadows that made smaller creatures scramble for cover. Predation wasn't just a threat, it was a certainty. And yet, down in their burrows, these whiskered pioneers played a different game. They survived heat waves by staying underground. They weathered volcanic winters by huddling together for warmth. They foraged at night while giants slept. In their own quiet way, they were building resilience while the dominant rulers of Earth gambled everything on size and power. Science offers us a striking clue. In the fossil record, many large Triassic reptiles vanish suddenly, their remains marking extinction pulses. But the tiny ancestors of mammals endure. Why? Because their biology was flexible. They could shift diets, hide in networks of tunnels, and reproduce faster than the giants could recover. In the story of life, sometimes small and adaptable beats mighty and dominant. This is where the arc of history tilts. Above ground, dinosaurs were rising toward dominance. But underground, a quieter story of endurance was unfolding. The whiskered, warm-bodied, socially curious creatures didn't just survive the chaos, they learned from it. They became the blueprint for a lineage that would one day inherit the Earth. But here's the real twist. What hidden adaptations allowed them to cling to life when others perished? Was it their bodies, their brains, or something deeper in their evolutionary code? It turns out the key wasn't just in being small, it was in being different. Deep inside their bodies, these proto-mammals carried survival tools that most Triassic giants simply didn't. First was metabolism. Unlike reptiles, whose energy ebbs and flows with the sun, early mammal ancestors were shifting toward a more stable, internally regulated warmth. Even if the skies turned dark with ash, even if nights stretched cold and long, they could keep moving, keep foraging, and keep raising their young. In an unstable world, internal stability was a game-changing advantage. Second was reproduction. While massive reptiles laid clutches of eggs vulnerable to heat, predators, and sudden climate swings, mammal-like creatures leaned into shorter cycles and smaller broods. They could replenish populations quickly. That meant even if disaster wiped out half a colony, the survivors could bounce back within just a few seasons, something their giant rivals could never match. And then there was sensitivity. Fossil skulls reveal early evidence of enlarged inner ears and more complex jawbones. These weren't just quirks of anatomy. They were steps towards sharper hearing, finer control of chewing, and, eventually, the ability to process new sounds. Imagine huddling in the dark and sensing the faint vibrations of a predator outside, or detecting the soft rustle of insects underground. Awareness meant survival. What's remarkable is that these edges weren't obvious in the fossil record until scientists began piecing together clues with modern imaging. It's as if the story of survival wasn't written in the towering skeletons displayed in museums, but in the tiny anatomical details hidden in fragile bones. This changes the way we see the Triassic. Survival wasn't only about who ruled the land under the sun, it was also about who could endure the dark. And these whiskered pioneers, barely larger than a rat, were quietly crafting an evolutionary toolkit that would echo through the ages. But here's the question that lingers. Did these adaptations guarantee their future dominance, or were they just buying time in a world still belonging to the dinosaurs? Above ground, the world looked very different. While our small, furred ancestors scurried in the shadows, dinosaurs were rising to claim the open stage. In the aftermath of the Permian extinction, ecosystems were empty, ripe for colonization, and dinosaurs, fast-growing, efficient, and increasingly diverse, marched into that vacuum like an unstoppable tide. Picture it. The Triassic plains stretched wide, dotted with ferns and conifers, rivers carving through shifting deserts. Herds of early sauropodomorphs, long-necked plant-eaters, grazed in clusters, their sheer size enough to deter most threats. Carnivores like Coelophysis darted between them, lean and agile, hunting in coordinated packs. The Earth was reorganizing itself around these new rulers. Dinosaurs weren't just lucky. They carried their own suite of advantages. Hollow bones made them lighter, fueling agility and speed. Rapid growth cycles allowed juveniles to reach maturity quickly, reducing the years of vulnerability their giant rivals once faced. And their hips, structured in a way that supported upright walking, freed them to dominate both speed and endurance on land. For millions of years, these giants towered over the world's landscapes, seemingly unchallenged. They weren't just surviving, they were thriving, spreading across Pangaea, diversifying into forms that could adapt to nearly every niche available. But here's the irony. While they seemed destined for eternal dominance, their story was balanced on a knife's edge. For all their grandeur, dinosaurs were exposed to climate swings, to food scarcity, to the delicate balance of ecosystems that depended on stability. Down below, in the leaf litter and burrows, our mammal ancestors faced none of these vulnerabilities. They thrived in shadows, while dinosaurs blazed in the sun. Two parallel experiments in survival were unfolding. One loud, colossal and spectacular. The other quiet, hidden and patient. And as we trace this story forward, the contrast only grows sharper. Because the question isn't simply how dinosaurs rose, it's how mammals, despite being dwarfed and overlooked, held onto a thread of resilience that would one day flip the balance of power.
While the dinosaurs ruled the plains, skies and forests, the story underground was no less dramatic. Early mammals, small, nocturnal, sharp-sensed, were carving out lives in the spaces dinosaurs didn't dominate. Imagine burrows tucked under ferns, nests hidden in tree roots, and quick flashes of fur darting out only under the cover of darkness. Here's the remarkable part. Mammals weren't competing with dinosaurs. They were avoiding them. By adopting a nocturnal lifestyle, they found a niche that kept them largely invisible to the reptilian rulers above. Their large eyes adapted to low light. Their whiskers became sensory tools, mapping the world through touch. Their ears, already evolving into structures more sensitive than those of reptiles, could pick up the faintest rustle of insect wings. This night shift wasn't just survival. It was innovation. Mammals were testing evolutionary tools that dinosaurs largely ignored. While dinosaurs honed size, speed, and strength, mammals doubled down on brains, senses, and flexibility. They ate insects, plants, even small reptiles. They could shift diets when food grew scarce, something their giant counterparts struggled to do. And in this hidden world, a strange balance took hold. Dinosaurs may have been the rulers, but mammals were the quiet survivors, experimenting with traits that seemed insignificant at the time. Warm blood gave them the ability to regulate body temperature in fluctuating climates. Fur insulated them from cold nights. And most importantly, they were beginning to invest in parental care. Fewer offspring, but each nurtured with greater success. Think of it this way: while dinosaurs lived fast and burned bright, mammals lived carefully and endured. One path led to spectacle, the other to resilience. Neither was wrong. Both were powerful strategies. But history favors patience, and the mammal's quiet endurance, evolving in the shadows of giants, would one day prove decisive. Because when the world shifted again, when catastrophe swept the dinosaurs aside, it was the traits forged in secrecy, in darkness, that allowed mammals not just to survive, but to inherit the earth. Picture this. A small, shrew-like mammal darts from its burrow at dusk, the air still heavy with the scent of ferns. Above, the ground trembles, not from an earthquake, but from the casual steps of a dinosaur grazing nearby. These two creatures, worlds apart in scale, were bound together by the same fragile ecosystem. Mammals and dinosaurs rarely met on equal terms. When they did, it was usually deadly for the mammal. Yet these encounters were important, shaping the way mammals evolved. Fossil evidence shows that some mammals developed powerful bites compared to their size, capable of crushing insects and even gnawing on small reptiles or eggs. Others grew faster reflexes, their nervous systems wired for rapid escapes. Every brush with a dinosaur was a test, and only the quick, clever, and adaptable survived. There's a fascinating twist here. Mammals sometimes turned predators themselves. Fossil discoveries from China show evidence of mammals large enough to hunt small dinosaurs. These weren't giant beasts, but cat-sized hunters with sharp teeth and surprising agility. For the first time, the balance tilted ever so slightly. Mammals weren't just hiding, they were learning how to strike back when opportunity allowed. And this edge-of-the-world relationship drove a quiet arms race. Dinosaurs got bigger, but mammals got smarter. Dinosaurs laid dozens of eggs at once, but mammals poured energy into raising fewer, more capable young. Dinosaurs roared across the daytime, but mammals mastered the twilight and the night. The two strategies shaped the entire Mesozoic world. On one side, overwhelming power and dominance. On the other, patience and adaptability. And though the dinosaurs may have seemed unshakable, nature was quietly hedging its bets, nurturing these small survivors who were writing their own evolutionary playbook. The question becomes, what happens when dominance falters? When the rules of the game suddenly change? Because history shows us this. Power alone isn't enough when the world itself tilts. And soon, mammals would face a test that even dinosaurs could not pass. The ground beneath those ancient forests was not as steady as it seemed. The age of dinosaurs looked eternal, but the earth has never respected permanence. Beneath the crust, giant forces were stirring, volcanoes that could poison skies for centuries, shifting continents that tore apart ecosystems, and oceans that rose and fell in great pulses of extinction. For mammals, these shifts were crucibles. While dinosaurs often thrived in stable, lush environments, their massive bodies and enormous appetites made them vulnerable to sudden scarcity. Mammals, by contrast, were like evolutionary gamblers with smaller stakes, flexible diets, quicker breeding cycles, and bodies that demanded far less to survive. When droughts, scorched jungles, or volcanoes clouded the sun, the giants struggled, but the little ones endured. And then came the ultimate tilt of the board. An asteroid, 6 miles wide, striking Earth with the force of billions of atomic bombs. Forests burned, oceans boiled, and the sky turned black. For the great dinosaurs, there was no adapting fast enough. But in the tunnels and undergrowth, mammals clung to life. This was not luck, it was preparation. The very traits honed in the shadows: night vision, opportunistic diets, shelter-seeking instincts, suddenly became the keys to survival. While titans toppled, the overlooked survivors stepped into a world reset. It's easy to imagine the silence after impact. No more thunderous footsteps, no more reptilian dominance, just ash settling over a broken earth. But within that silence, small heartbeats carried on, hearts that would give rise to every mammal you know today, including us. And here's the real story. Without those ages of hiding, without those forced adaptations at the edges of dinosaur power, mammals would never have been ready for this moment. The age of shadows prepared the architects of the next age, the mammals destined to inherit the earth. But this raises a question that reshapes our understanding. Did mammals merely survive by chance, or was their survival built into their design, the culmination of millions of years of quiet preparation beneath the feet of giants? Imagine the morning after the asteroid's fury. The skies were still dark, the forests still smouldering, and oceans still trembling with aftershocks. But somewhere in the ash-choked silence, a mammal emerged from hiding. It wasn't majestic, it wasn't a conqueror, it was small, furry, insect-eating, hardly remarkable by any prehistoric standard. But in that fragile step across a devastated landscape, Earth's story pivoted forever. For the first time in 160 million years, the dominant rulers of the land were gone. Dinosaurs, once the architects of ecosystems, were now reduced to fragile bird lineages. The throne of dominance stood empty, and into that vacuum crept mammals. Here's where the science becomes fascinating. In the fossil record, paleontologists find clear evidence of what's called adaptive radiation, Within just a few million years after the impact, a blink in geological time, mammals exploded in diversity. Species that once barely dared to evolve into new forms suddenly branched into predators, grazers, climbers, and swimmers. The earth was open for reinvention, and mammals seized it with astonishing speed. Picture an earth reshaped, forests regrew across continents, new rivers carved valleys, and with every fresh ecosystem, mammals filled the gaps. Some grew larger, testing the size limits now that dinosaurs no longer loomed. Others became specialists, gliding through trees, burrowing deeper into soil, fishing in rivers untouched by reptilian giants. The age of mammals had begun, not in triumph, but in quiet, steady persistence that suddenly turned unstoppable. And what's more, their rise wasn't random. Everything they had practiced in obscurity, flexibility, speed of reproduction, night vision, varied diets, became the exact tools needed to rebuild Earth's web of life. It was as if evolution had been rehearsing mammals for this stage all along. But if mammals now owned the day, what happened next would shape them into forms that still walk beside us. From rodents to whales, from primates to hoofed giants, the next chapters would unfold like a burst of creative energy from nature itself. And that sparks a new question. Why did some mammals stay small and hidden, while others leapt into roles as giants, predators, and even ocean titans? The answer lies in the choices Earth forced upon them, choices that would define the path to us. From the shadows of small beginnings, mammals didn't just survive. They began to dream bigger. The fossil record tells us something astonishing. Within a few million years after the asteroid wiped away the dinosaurs, mammals were already pushing the limits of size as though Earth itself whispered, "Fill the space they left behind," and so they did. On the open plains of Asia, a creature called Indricotherium, a relative of the rhinoceros, rose to stand over 16 feet tall at the shoulder. Taller than a giraffe, heavier than an elephant, it was a living skyscraper of the Cenozoic. Imagine walking through scrub forests and looking up at a giant so massive it could browse treetops the way a giraffe nibbles acacia leaves today. These were the new titans of Earth, reclaiming the scale once reserved for dinosaurs. But the Earth didn't stop there. Some mammals took to the seas, evolving into forms no one could have predicted. Picture a wolf-like creature, Pachycetus, padding along a riverbank. Within a few million years, its descendants slid fully into the oceans, becoming the ancestors of whales. By the time of Basilosaurus, a serpentine whale longer than a school bus, mammals had not only conquered land, but had reinvented themselves as rulers of the oceans, filling the void left by marine reptiles like the mosasaurs. What makes this chapter so mesmerizing is the sheer speed of the transformation. Where dinosaurs had needed tens of millions of years to reach their dominance, mammals did it in evolutionary overdrive. Scientists call it one of the most dramatic adaptive radiations in history. A biological fireworks display in which every possible niche was tested. The seas, the skies, the trees, the grasslands. Mammals were no longer background actors. They were rewriting the script of Earth's story. But the giants weren't the whole tale. Alongside them thrived smaller, cleverer mammals. Primates beginning their cautious climb through trees. Rodents mastering survival strategies. Carnivores sharpening their skills. These were the seeds of lineages that would one day lead to us. And here's the thought that should make you pause. Evolution wasn't just restoring balance. It was setting up a new world order. Every choice, every adaptation, every leap into the unknown was stacking the dominoes toward a future where intelligence, not size, would rule. So the real question becomes, how did this age of mammals, with its giants and innovators, set the stage for the rise of creatures capable of questioning the universe itself? As giants thundered across plains and whales carved out dominion in the seas, something far subtler was happening in the canopy above, not as dramatic, not as imposing, but far more consequential. The primates, small, wide-eyed and nimble, were beginning to map a different kind of destiny. In the tropical forests of the Paleocene and Eocene epochs, trees became laboratories of innovation. Early primates like Natharctus darted between branches, their grasping hands and stereoscopic vision giving them an advantage no grazing giant could ever claim. Depth perception, precision, and an ever-expanding ability to interact with the world in 3 dimensions. These weren't creatures built to dominate by size. They were built to perceive, and here lies the turning point. While Indracotherium towered and Basilosaurus swam, primates were wiring their brains for problem-solving, social complexity, and adaptability. Fossils show gradual but critical shifts, skulls that allowed for larger brain capacity, teeth suited for varied diets, joints designed for agility and curiosity. Evolution was quietly investing in intelligence while the rest of the world marveled at power and scale. It's easy to overlook them. Who would think that a lemur-like creature clinging to a branch in some forgotten forest would hold the keys to the future of Earth? But history whispers a warning. Dominance isn't always written in bones and muscle. Sometimes it's written in neurons, in the subtle shaping of perception and awareness. And as climates shifted, forests thinning, grasslands spreading, primates proved their resilience. They weren't locked into one role. They could shift, adapt, evolve. This flexibility became their survival superpower. Think of it this way. While the age of mammals dazzled with giants, the true revolution was invisible, happening one synapse at a time. Every leap through the branches, every new way of seeing and grasping was laying down the neurological groundwork that tens of millions of years later would allow a species to look up at the stars and ask questions about the universe. So while Indracotherium vanished and Basilosaurus disappeared, these small, adaptable primates carried forward the seeds of curiosity, seeds that would grow into something Earth had never seen before, a creature that didn't just survive, but sought meaning. And that begs the question, when did survival give way to wonder? When did the climb for fruit and safety turn into the climb toward knowledge, art, and science? The story of primates is not just about agility in the trees, it's about pressure, unyielding, relentless, invisible pressure, the kind that doesn't roar like a predator or crash like a meteor, but shapes every living thing just the same. That pressure was climate. Around 34 million years ago, Earth shifted dramatically. Global cooling marked the end of the Eocene. Vast forests that once blanketed continents began to retreat, shrinking back as open woodlands and grasslands expanded. For primates, it was a test unlike any before. Their leafy laboratories, those ancient rainforests, were disappearing. The branches that had nurtured their evolution for tens of millions of years were thinning, fragmenting, vanishing. This was the crucible. Some primates clung desperately to shrinking forests and vanished with them, but others adapted, developing new diets, new social structures, and new ways of moving through a changing world. Fossil evidence reveals species like Egyptopithecus, an early monkey-like primate from North Africa, bridging the gap between smaller arboreal ancestors and the lineage that would eventually radiate into apes and humans. But here's the breathtaking twist. Climate didn't just winnow species, it sharpened them. The ones who endured became more versatile, capable of thriving on tougher foods, navigating mixed environments, and forging complex group dynamics. Survival wasn't about who was strongest, but who could adapt when the ground shifted, literally beneath their feet. And in that struggle, primates gained something new, resilience built into their very biology. Larger brains, greater cooperation, a flexibility of behavior that no giant, no specialist grazer or hunter could ever hope to match. Climate was chiseling them, sculpting them into the kind of animal that could not only endure change, but turn it into opportunity. Pause and consider this. The very conditions that seemed like disasters, forests collapsing, temperatures dropping, ecosystems shattering, were the forces that forged the ancestors of modern apes, and ultimately, us. Without upheaval, there might never have been curiosity, intelligence, or the spark of consciousness that defines our species. So the question becomes, is catastrophe the true engine of progress? Did the harshness of shifting worlds set primates and eventually humanity on the path from survival to significance? Out of that crucible of climate change, a new kind of primate emerged. Not quite like the small, scampering monkeys of the earlier epochs, and not yet like us. These were the first true apes, and they would change the course of evolution forever. Around 20 million years ago, during the Miocene epoch, tropical forests returned in parts of Africa and Eurasia, but the primates that now filled those forests were not the same as the ones that had survived the Eocene collapse. They were bigger, stronger, and far more versatile. Their bodies told the story of change, flexible shoulders for swinging through branches, robust jaws for crushing tougher foods, and brains just a little larger than their predecessors. This was the age of Proconsul, one of the earliest known apes. Fossils show a creature that looked like a bridge between monkeys and the great apes. No tail, a more upright posture, and the beginnings of the adaptations that would one day make climbing, tool use, and even walking possible. Proconsul wasn't alone. The Miocene was a golden age of ape diversity, with dozens of species exploring evolutionary possibilities across continents. Some developed powerful arms and torsos for climbing. Others evolved teeth and jaws specialized for fruit, leaves, or even seeds. But here's where the story sharpens. Not all of them would last. The very success of apes sowed the seeds of competition. As environments shifted yet again, grasslands expanding, forests receding, many ape lineages dwindled and vanished. Only a handful adapted, laying the groundwork for what would become gorillas, chimpanzees, orangutans, and humans. And yet, imagine the scene. Miocene forests alive with experimentation. Apes of all shapes and sizes, testing evolutionary strategies like notes in a symphony. Some were giants, creatures like Gigantopithecus, a towering ape that stood nearly 3 meters tall. Others were small and nimble, darting through canopies. It was a world of possibility, and for millions of years it seemed apes might dominate Earth the way dinosaurs once had. But nature has no patience for permanence. The Miocene ended, climates shifted again, and once more most lineages vanished. What survived was not the biggest or strongest, but the ones best able to adapt, to change their diet, their movements, their social bonds. Those survivors carried within them the blueprint for the future, the intelligence, dexterity, and cooperation that would one day ignite into humanity. And here's the cliffhanger. If climate forged apes, what pressures would it take to shape the first humans? The story narrows. Out of that dazzling diversity of Miocene apes, only a few would survive the grinding test of climate and time. By around 7 million years ago, the stage was set for something extraordinary. The first hominins, the earliest ancestors of us. But it didn't happen in a lush jungle. It happened in places where the forest was thinning, where open woodlands and grasslands were spreading under skies that were growing drier. In this changing world, survival demanded something new. Here enters Sahelanthropus chadensis, discovered in the deserts of Chad. Its skull is small, barely larger than a chimpanzee's, but its features tell a different story. The position of its foramen magnum, the hole where the spine connects, suggests it held its head upright, a hint of bipedalism. That shift from knuckle walking to tentative steps on 2 feet may have been the single most consequential gamble in the history of life. Why walk upright? Scientists still debate. Some argue it freed the hands for carrying food or tools. Others suggest it was a way to conserve energy across vast distances or to peer above tall grasses to spot predators. Whatever the reason, those early steps reshaped everything: body, brain, even society. Standing tall opened a door no other animal had ever walked through. Other early hominins soon followed. Auroran tuganensis in Kenya, known as the Millennium Man, shows thigh bones adapted to upright walking. Ardipithecus, a million years later, blended traits of tree climbing with the mechanics of bipedal life. They weren't yet human, not in body, not in mind, but the template was forming. And with bipedalism came vulnerability. Walking upright made hominins slower runners, weaker climbers, and more exposed to predators. Yet what they lost in strength, they gained in adaptability. Free hands meant the possibility of shaping the environment, using sticks, stones, maybe even crude shelters. Each generation that survived carried this strange experiment a little further. Now imagine the scene. Scattered bands of hominins on the African savanna, standing upright under burning suns, watching herds of antelope and packs of lions. They are small, fragile, unremarkable in the animal kingdom, yet holding within them the seed of what would become art, language, and science. The question becomes, how did these vulnerable creatures endure long enough to matter? The answer lies not in muscle, but in mind. And that is where the next chapter begins. Picture those early hominins, small groups huddled beneath acacia trees, scanning the horizon for predators, clutching whatever food they could scavenge. They weren't just surviving, they were beginning to think differently. By around 4 to 3 million years ago, species like Australopithecus afarensis, the famous Lucy, walked fully upright. Their brains, though still small, were subtly reorganizing. We can see it in the shape of their skulls, folds for areas linked to planning, coordination, and social memory. Evolution wasn't just sculpting bone, it was wiring possibility. Walking on 2 legs had freed their hands. Now those hands began to explore. Simple stones were picked up, used to crack open nuts or bones. A shard with a sharp edge could tear meat. Nothing we would yet call tools, but hints of innovation were stirring. Each experiment left an imprint, not only on the landscape, but on the brains of those who wielded them. But raw intelligence alone wasn't enough. Survival on the savannah demanded something greater: cooperation. A lone Australopithecus was easy prey for leopards or hyenas, but together, watching, warning, sharing, they stood a chance. Here lies the deep root of what would eventually become language. Before words, there were gestures, vocal calls, maybe rhythms of movement that conveyed intent. Communication was survival.